All right, so we're going to finish up today with section 3.2. Okay, be the last section that's on our test. And first thing we're going to look at is the different ways you can write a proof. Okay, so there's several different ways you can write a proof. Okay, the way we've been sticking with quite a bit is the two-column proof. That's where you put your statements one side, your reasons in the other. We did do another example of a different type of proof. Anybody remember what that one was? Yeah?
A paragraph proof?
Yeah, we did a paragraph proof. That's where you just write out your sentences and you just explain, what's happening. If you have a two-column proof, it's very easy to change that to a paragraph proof. You just start to use complete sentences and it becomes a paragraph proof. And there's one other kind of proof that we don't really focus on, and it's called a flow proof. Okay, I'm going to show you an example of a flow proof. If you have any homework problems that say write a flow proof, you could do a two-column proof instead. Okay? But let me show you what a flow proof is. Yeah. A flow proof looks more like a diagram. And what you do is you draw arrows that kind of show the logical flow of an argument. Right, so a lot of times we'll have a box. In the box will be a statement. And then the reason for that statement is written, you can write it just above or just below the box. And then you have an arrow, and that arrow says this leads to the next statement. Okay? So it's an example of something that's a flow proof. Okay, now, some of the properties here you don't know yet. Okay, you haven't learned some of these theorems that have to do with triangle congruence. Okay, we're going to get to this in later chapters, but not even chapter 3. We're not going to get to it yet. All right, so there's some information here that was probably given. Maybe they gave coordinates, and the person used the distance formula to find the distance between point C and point B, and they got 5. And then point D and point B, and they got 5. Okay, the first step should be okay. If CB equals 5 and DB equals 5, then CB and DB are the same length. The reason? I've used substitution, or you could also say transitive property of equality. Okay, next, if you have two segments that are equal in measure, that means they are congruent. That's the definition of congruent segments. Okay, so this is kind of like one branch of the flow proof. Okay, and all of that information is going to lead, this is the conclusion right here. But there's several ideas that are coming into that conclusion. Let's look at some of the other stuff. Okay, now this is going to be a little harder because we don't know about congruence with triangles yet. But there was something that was given here. These angles were both right angles. Okay. So that was given. And this statement, I think you'll understand. If you have a right angle and a triangle, it means it's a right triangle. That's the definition of what it means to be a right triangle, if you have a right angle. Okay, so then they're saying that. Then there was another piece of information that was given, and together, kind of this branch and this branch, these three things are leading to this conclusion right here. That triangle ADB and triangle EBC are congruent. And this is called the hypotenuse leg theorem. We'll learn that.
Are we going to have to prove it since you tentatively proved it?
Well, yeah, I'm not really going through anything formal here because we're using concepts that are until chapter 4 and 5 in this proof. So the idea here is I just wanted you to see what a flow proof looks like, even if you don't understand all the reasons. I hope you understand the top part. Maybe not the bottom part, but. Okay, so that's called a flow proof. Again, generally, we're not going to focus on writing them this way. But some people like it because it's more visual. Okay, we're going to look at a few different theorems about perpendicular lines. Okay, about 3 of them. All of these theorems are on page 137. Okay, so if you want to copy them down now, you can. If you want to go back and look at 137, you can do that too. What I'll try to do first is just describe the theorem, and then I'll draw you a picture of it. So this theorem says if two lines intersect to form a linear pair of congruent angles, then the lines are perpendicular. Okay, so it's important here you remember what linear pair means. Linear pair means you have two angles that are adjacent. Adjacent means that they share a side and a vertex. So two angles that are adjacent, and the sides that they don't share form opposite rays. That's a linear pair. Okay, so here's an example. If I just draw a linear pair, okay, there's one angle. Now I have to have another angle that shares a side, shares a vertex, and the ray that they don't share has to point in the opposite direction. So the blue angle and the red angle, those are a linear pair. So now we're extending that a little bit to say that if the angles form a linear pair and they're congruent, here they're not congruent. The red angle is a lot bigger than the blue. But if they were congruent, that would mean the lines are perpendicular. Right? And we'd have to reason through why that's true if we're going to prove that. Okay, we'll prove this one. Okay, so there's an example of a linear pair where the angles are congruent, and that proves G is perpendicular to H. Okay, if you haven't seen this symbol before, I think we already did it, but this upside down T means perpendicular. All right, so Theorem 3.2. Okay, Theorem 3.2 says that if two sides of two adjacent angles are perpendicular, then the angles are complementary. Okay, let's compare that to Theorem 3.1. They seem kind of similar. In fact, if you look at the conclusion in 3.1, then the lines are perpendicular, that becomes the hypothesis in statement 3.2. Basically, okay, if two sides of two adjacent angles are perpendicular. So if you have two sides that are perpendicular, that's at the beginning. If you have two sides that are perpendicular, it was at the end of Theorem 3.1. Okay. So there's a little bit of a relationship here. So if two sides of two adjacent angles are perpendicular, then the angles are complementary. Okay, here's a picture. Right, so angle 1 and angle 2 are adjacent. They share a side. They share a vertex. And the two sides that they don't have in common, this one and this one, are perpendicular. Then that means angle 1 plus angle 2 would have to add up to 90 degrees. There's no other way that could happen. Okay, so that's Theorem 3.2. Probably won't go through the proof of that one. We could, but we'll look at this one. Okay, if you have two lines that are perpendicular, then they intersect to form four right angles. Okay, I mentioned that idea earlier to you. Okay, so I might let you try that one on your own a little bit. Theorem 3.3. Okay, if two lines are perpendicular, then they intersect to form four right angles. All that we know if two lines are perpendicular is that they intersect to form a right angle. We haven't proven yet that every other angle here is automatically a right angle. Okay, but in a few steps, talking about congruence, maybe vertical angles, you could show that. And we'll do part of it. at least you're part of it. Okay, any question on theorems 3.1, 3.2, or 3.3? Yes?
Would it be 4 separate rays, essentially, because the center, the vertex of the 2 lines would technically be opposite rays?
Yeah, technically, when you have an angle, angles are made up of rays. So if you have 4 angles here, yeah, really it's like having 4 rays.
Because if it's
Yeah.
perpendicular, it's not intersecting all the way. You would have to have another ray.
Yeah, so yeah, for each angle you have here, think of each angle is made up of, say the angle in the upper right, that's a ray, and that's a ray. Okay, we're looking at it as lines because that's what the theorem is about. But technically you're right, when we did define angles, we defined it an angle to be made up of 2 rays. Yeah. Okay, you don't have to know the theorem numbers. Okay, in fact, on a test, I'm not even going to use these. All right, if you have to reference this theorem, you're just going to have to write it out. All right, because it's too difficult to try to remember what theorem is what number. Let's start off with theorem 3.1. Okay, so it's theorem 3.1. You're given a couple things here. Angles 1 and 2 are congruent. And angles 1 and 2 are a linear pair. Okay, so we might have to think back and remember exactly what it means to be a linear pair, or a fact that comes directly from that. I want you to prove G and H are perpendicular. Okay, what I haven't done this time is I haven't listed everything in the given, because there's some facts that I can prove just by knowing angles 1 and 2 form a linear pair, and I don't need to know that they're congruent yet. All right? I'm going to get to a point in this proof where I need to know that, and when I need to say that, I'll say it at that time. Okay, so this is going to be one of our first proofs where we don't list everything that's given right away because it might confuse the reader. Okay, generally, if you say everything that's given right away, that's because you're going to use it all right away. But if you write something that's given and you don't use it, somebody reading it would wonder, well, why did they write that if they're not using it yet? So don't write what's given until you need it. Okay, let's give this a shot. Okay, so angles 1 and 2 form a linear pair. What does that mean? Just in general, if 2 angles form a linear pair, then they are what? Okay, they're on the same line. Yeah, kind of getting at what I'm looking for. It's actually 2 things I'm looking for. We got to say one before the other.
They are congruent.
Well, we know 1 and 2 are congruent. That's given, but I don't need that fact right now.
If it forms a linear pair, it's congruent.
Not necessarily. Remember what I drew in red and blue. Those are linear pair. So linear pair doesn't necessarily mean congruent. It just means that you have 2 angles that are, and there's a word for it.
That's supplementary.
Exactly, yep. It means angles 1 and 2 are supplementary. Okay, that's all we know. They are supplementary. The reason? That's the definition of a linear pair. All right. Now, what else do we know? Let's use that fact. We have 2 angles that are supplementary. What does that mean? Almost just using the definition of supplementary. Yeah?
They equal 180.
Angle 1 equals 180 and angle 2 equals 180?
Angle 1 and 2 equal 180 separately. So 1 I don't know how to phrase it.
So we've got to be careful. Don't say angle 1 and angle 2 equal 180. Together they,
So angle 1 is
yep,
measure of angle 1 and measure of angle 2 equals 180.
no. The measure of angle 1 and the measure of angle 2 do not equal 180. That's what was just said. Measure of angle 1 and measure of angle 2 both equal 180. Yep,
The measure of angle 1 and measure of angle 2 add up to?
there you go. They add to 180, yes. So you can say that they add up to 180, their sum is 180, however you want to say it. I'm just going to write it like this. As an equation. Measure of angle 1 plus measure of angle 2 equals 180. Okay, but you're all on the right track. Okay, you just got to be a little bit more specific when you write a proof. Okay, and that's the definition of supplementary angles. Okay, any question up to that step? Right, now I think we've done everything that we can do with the first statement that was given. Now I need that other fact. Okay? I need this fact. Angle 1 and angle 2 are congruent. Okay? I'm going to come back to step 3. I'm going to go somewhere with that, but I can't until I use that other piece of information. Okay, so angle 1 is congruent to angle 2. What's my reason for that? That's given. Okay, and what does that mean? If angle 1 and angle 2 are congruent,
The measure of angle 1 plus the measure of angle 2. Now the measure of angle 1 is equal to 90.
measure of angle 1 equals the measure of angle 2. All right, and that's the definition of congruent angles. Definition of congruent angles. Now we're ready to go back and take something we did in step 3 and step 5 and put them together. Anybody see how I can combine step 3 and 5 to get step 6? I know that measure of angle 1 plus measure of angle 2 equals 180. And I know the measure of angle 1 equals the measure of angle 2. Anyone see what we could do there? Mm-hmm.
The measure of angle 1
Mm-hmm.
is equal to 90. I don't know how to...
That's what we have to get to. But it's something we have to say first. So they want to show us, once you show that the measure of angle 1 is 90, then you can say that that's a right angle, and by the definition of perpendicular lines, G and H are perpendicular. So that's what we have to try to get to. But once we get that the measure of angle 1 equals 90, we're good. Anyone else see what we can do? Okay, well, here I have the measure of angle 2, right? What's the measure of angle 2 the same as? The measure of angle 1. So change measure of angle 2 in step 3 to measure of angle 1 because they're the same. So you have measure of angle 1 plus measure of angle 1 equals 180. What's the reason for that when you change something? That was substitution. And now we've almost got that measure of angle 1 equals 90. Okay? What I'm going to do in this step is just going to be called simplify. Measure of angle 1 plus measure of angle 1. How many angle 1s do I have? 2 of them. It's like if you had x plus x, that's 2x. Okay? The measure of angle 1 plus measure of angle 1, that's 2 times the measure of angle 1. Okay, that we'll just call, you could call it the distributive property, or I'm just going to say you simplified. Okay. Now the next step, I'm going to write measure of angle 1 equals 90. Why? What did I do?
divide 180 by 2.
Yeah, this is the division property of equality. Divide both sides by 2. So division property of equality. And now if the measure of angle 1 is 90 degrees, what kind of angle is angle 1? Angle 1 is a right angle. Angle 1 is a right angle. Reason? That's the definition of a right angle. Definition of right angle. All right, now, since I know angle 1 is a right angle, that proves G and H are perpendicular. Because that's the definition of perpendicular lines. They form a right angle. So what was it? G and H? Reason, definition of perpendicular lines. Okay, so this is a good proof in the sense that it's somewhat technical. You have to say a lot of things here, a lot of simple things, but they have to be said in a certain order to make it correct. Okay, so far this is probably one of the most technical proofs that we've done in terms of what you have to say and how you say it. But any questions on any of the steps of that? Okay, and it's hard if you try to do this all in your head and you just try to think of every step beforehand, you kind of get stuck. I didn't think this proof was going to have 10 steps at all. I thought it was a lot shorter than that. But as I kept going, one fact just kept leading me to the next. You know, I'm going to divide, and then I get a 90, and if it's a 90, it's a right, and if it's a right, you got perpendicular lines.
Yeah, you like combine some steps though.
You might be able to combine a little bit, but this is the clearest way to write it so people could see every single step one at a time. But sure, there's always other ways to do a proof. Yep. In fact, the book did this one as a flow chart. Okay, they did it as a flow chart. Okay, any question on that? So that proves theorem 3.1. Now, if you ever want to use that theorem in the future, you can just use it. You don't have to prove it. Now we know that if you have a linear pair of congruent angles, you have perpendicular lines. That's a fact we can use. Okay, that theorem won't really help us here. That theorem is what you would use to prove that you have perpendicular lines. I'm telling you right up front you have perpendicular lines. You don't have to prove that. Okay, I'm telling you L is perpendicular to K. What I want you to prove is that angles 1, 2, 3, and 4 are all right angles. Okay, so give that one a shot on your own. See if you can try to come up with the steps. If we can't get through all of it, that's okay, but just try to do some of it. And see if you can prove all those angles are right angles. A couple hints, you might want to think about using vertical angles being congruent. That could help out. Okay, but I want to prove that they're right angles. So if you prove that they're all 90, that's good. But then you'd have one more step to say they're right angles by the definition of right angles.
So you're doing a proof, and you know how we did like constructions yesterday about how you can make a right angle? Could your proof be like, if I put a dot like right on this line and then, you know, do the construction for it? Could that be a proof for like, you know?
Well, so the construction we did yesterday basically allows you to construct, if you have a point and a line, and a point not on that line, it enables you to construct perpendicular lines. Now, I'm already giving you that you have perpendicular lines. So, I mean, you could try to think about how you could use that. I'm not sure if you could in this proof. But you certainly could try to think about it, give it a shot, and see what you can do with it. If you find it's making your proof too complicated, you might just want to not use that fact. Okay, so I've started you off with the statement and the reason, and see what you can do from there. All right, so we're trying to prove that L and K are perpendicular. All right, so by the definition of perpendicular angles, what we're allowed to do is pick one of these angles to be a 90. Let's say it's that one. Okay? Angle 1 is a right angle, and that's the definition of perpendicular lines. And we were given that we had perpendicular lines. Okay, so let's start with that. So angle 1 is a right angle. And 2, reason, definition of perpendicular lines. All right. Next statement. If angle 1 is a right angle, what else does that mean? If it's a right angle, then right angle means what? Yeah, its measure is 90. Measure of angle 1 equals 90. That's the definition of a right angle. Okay, next step. I'm going to say that the measure of angle 4 equals 90. What's my reason for that? Let's see. 1 and 4 aren't adjacent.
No, vertical.
They're vertical. Okay, good. Now, if angle 4 is 90, what else does that mean about angle 4? It's a right angle. So, angle 4 is a right angle. Why? Because it measures 90 degrees. That's the definition of a right angle. Definition of right angle. Okay, now let's just kind of check off the angles we've proven. Okay, we've got angle 1 is a right angle by the definition. We've got angle 4 is a right angle. Now we need to talk about 2 and 3 somehow. Now I think if we can prove 2 or 3 is a right angle, then vertical angles comes in again. What kind of angles are 1 and 2 by that picture? Yeah?
Adjacent.
Yeah, they're adjacent. Okay, we know that they're adjacent because they share a common side. That would be the top part of line K. They share a vertex right there. And there's no way that a point could be inside angle 1 and inside angle 2 at the same time. Okay, so we know that they're adjacent. 1 and angle 2 are adjacent angles. Okay, that's the definition of adjacent angles.
They are adjacent.
Okay,
You also don't have to say.
next thing we know is that their non-common sides form opposite rays. I'm talking about that side and that side. So if they're adjacent and the non-common side forms opposite rays, that makes angles 1 and 2 what? Not supplementary, but a linear pair. Okay, that makes them a linear pair. Angle 1 and angle 2 are a linear pair. Now the reason part of it I just kind of explained to you, and you can look at the diagram and see it. It is the definition of a linear pair. We should probably formally state here, maybe as step 6b, which we didn't, is that the opposites, the non-common sides form opposite rays. What would be the reason for that? That's just looking at the diagram. Okay? I'm not going to write that step in, and I wouldn't be overly picky about writing that step. Okay. Definition of linear pair. Okay. Step 8. If angles form a linear pair, then that means they're supplementary. Angle 1 and angle 2 are supplementary by the definition of Yeah, supplement.
Quality repair.
Yep. Okay. In step 9, now we can get into the equation, which is probably where I'm going to stop. Measure of angle 1 plus measure of angle 2 equals 180. That's the definition of supplementary. And now you've already proven that angle 1 is 90. Substitute it in, then use the subtraction property, and then you'll get angle 2 is 90. And then once you know angle 2 is 90, by vertical angles, angle 3 is 90. And if they're 90, they're right angles. So there are a lot of steps in this proof. Okay, but I'm hoping you're starting to understand kind of the order of thinking when you do a proof. Okay, so you'd have to finish that one up. Okay, so for tonight, on page 138, I'd like you to try 3 through 9 all, 11 to 17 all, and 25 and 26. And for the MCAS, do open response number 1. Okay, and we'll take a look at that tomorrow before the test.